We will wait for 5 minutes for everybody to join, then we can start. So, so I think we can start. Is the screen visible? Okay, so we can start. So we will do first some MCQ based questions which are related to your this week's class, which was related to your how phase diagrams are formed, how we have diffusion happening in the system. So based on that, we will be trying to do some numericals. So the first question is that the Burgers vector is a measure of a magnitude of dislocation line, the magnitude and direction of a dislocation line, the direction of dislocation line, and the Miller indices. So you have to answer what is the right answer for this. I want you to answer the question. So what is the right option for this? Anybody can answer that question?
Magnitude and direction.
Okay, so right, the Berger vector is actually a common. It gives you about like a knowledge about your magnitude, the what is its magnitude, and the direction of the dislocation line. So usually you have seen it may be represented like this. It is the magnitude. So for example, uh, a by 2 is the magnitude, a under root of 2, and then you're also given a direction along which this Berger vector is. Say for example 110. So we have both magnitude and direction of a dislocation line given by a Berger vector, which is represented by like this B vector. Okay. Now another question says that which of the following are a two-dimensional defect? The edge dislocation, grain boundary, volume defect, or free surface. So you have only you have different types of defects. We have point defects, we have 1D defects, we have 2D defects, and we have 3D defects. So you have to say which among the following is not a 2D defect, which is a 2D defect. So edge dislocation, it is usually a linear defect. It is a 1D defect where you have like one lattice plane missing in the crystal structure. So you have a 1D defect. Grain boundary is also one of the defects where we have two grains coming together and then they create a defect because of their difference in orientation and because of their different atomic arrangement. So grain boundary, which is a 2D defect, and then we have volume defects and free surface defect. Free surface is also a 2D defect, actually, because we have one of the surfaces that is being exposed to the environment when you have a free surface. So you can have 2D defects, either is the grain boundaries, because volume defect by the name suggests it is a 3D defect, while the free surfaces are again the 2D defects. Okay. So next question says that the Berger vector of you have to say which of the following is right? So you have to say that the Berger vector of edge dislocation is parallel to dislocation line. Screw dislocation is perpendicular to dislocation line. Edge dislocation is perpendicular to dislocation line. Screw dislocation is inclined at 45 degree to dislocation line. So you have to say which of the following is right. You know that we have a Berger vector, it has a magnitude, it has a direction, and the direction is in a particular direction. It is based on the slip plane, based on your atomic arrangements. There is a plane that slips with respect to each other. So with respect to that slip line, on that slip plane there occurs a dislocation, and that is given by a Berger vector. For dislocations, we have two types, edge and screw. So you have to say what is the right option for this. How is the direction of a Berger vector defined for a screw and edge dislocation? So can you answer? Anybody can answer?
It is C, ma'am. Dislocation is perpendicular to dislocation.
Okay, so actually, yes, because we have this, we know that screw dislocation is not inclined to 45. This is a wrong option. The other option is that edge dislocation is parallel to dislocation. The right option is that it is perpendicular to the dislocation line when we are talking about edge dislocation. And then it says that screw dislocation is perpendicular to dislocation line. It is wrong because screw dislocation is actually parallel to the dislocation line. So the option C is the right option. Okay.
Madam, in the first question, the entity what you chose as A by root 2, that changes with the like lattice, right?
Yes,
If it
yes.
is FCC, yeah, FCC and BCC, it's going to change, yeah?
Yeah, it will change. You will be given a specific plane on which the slip is occurring or the dislocation is moving, and it is you
Okay,
will be given a direction through which whether it is parallel or perpendicular to that direction. Based on that, you
okay,
will find your Berger vector.
okay, yeah,
So
yeah,
yeah.
thanks.
Okay. Then we have another question that says that the defect associated with a mismatch of crystalline orientation from one grain to a adjacent grain is called a vacancy, a dislocation, a twin boundary, or a grain boundary. See, it is not a vacancy for sure, because vacancy is because of the difference in the atomic arrangement. That means in your atomic arrangement, if you have many atoms, there is a missing atom at certain position, that is called as a vacancy, right? So it has nothing to do with the vacancy. This is not a right option. Then it says that it is because of a dislocation. So also that is not possible, because we are talking about a mismatch in the crystalline orientation for a grain. We are not talking for an atomic arrangement, right? So dislocation is a mismatch of the lattice. It is a mismatch of the atomic arrangement, not of a grain. So this is also not right option. So the right option is grain boundary. and also because twins occur is just two parallel planes which are showing a mirror like images across a certain plane. So twin boundary can occur within a grain also. It is not from change of the orientation from grain to grain, but twin boundaries occur within the grains. So the right option is the grain boundary. Okay. So now we have some numericals to do. So the numerical is based on your vacancy, right? So we understand that what is vacancy. We have a atomic arrangement of atoms such as like this. So if you have a certain atom which is missing at a certain position, that is called as a vacancy, right? So this vacancy is actually, as you might have studied, that it is a temperature dependent phenomena. It has nothing to do with any other phenomenon of deformation or any other thing. It is because based on your thermal excitations, the certain atoms are getting removed from their lattice positions and they are creating a vacancy. So we are given that find out the ratio of vacancy concentration in a crystal upon increasing the temperature from 327 degrees Celsius to 527. So you are given a difference in temperature from 327 to 527, and you have to find what is the ratio of your vacancy concentration. Okay, so simply you have to utilize the formula that you are given, that number of vacancies at a certain point is equal to actually the normal number of lattice positions, and it is equal to e raised to power minus q by rt. Okay, so this is your formula. Now you have to find the ratio of vacancy concentrations at different temperatures. So you have to first convert the temperatures to your Kelvin scale. So your T1 will be equal to 327 plus 273, and this is 3, and then this we have T2, which is equal to 527 plus 273. Okay, so we have to convert both of them in the Kelvin scale first. So what are the two temperatures now in Kelvin? One will be 3, I think 600. The other temperature will be around 800, right? Now you have to calculate the vacancy concentration. So how will you do? You'll try to form two equations. So you have, say for example, for n1, we can have something, the same equation but at two regions. Okay, so this will be T1, and for another point we'll be having N2. So you divide the two equations. I think this is K actually, right? This is not R, this is K. So you can you have to find the ratio of the vacancy, that is you have to find N1 by N2. So you are given the temperatures, so you can solve it for the temperatures. So can you calculate it and tell me what is the value for your ratio of vacancies? So can anybody calculate what is the right answer? Can anybody calculate? You just have to put in the values of Q. Q is given because it is enthalpy of vacancy. So you are given Q. You have the two temperatures. So you have to do, you can do one thing. You can write it as e raised to power minus 14 because it is in kilojoules, so 10 to the power 3. And then you have 1 upon T1, which is 600, and 1 upon 800. Now can you calculate what is the right answer? Has anybody tried to solve the question? I think the right answer for this is A. You can try to calculate it and then see if you have got the same answer or not. Okay. So then we will move to next question. The question says, which of the following is a part of Fick's first law? Diffusion flux, concentration gradient is changing with position, concentration gradient is changing with time, and concentration profile is linear. So you have to say which of the following is the right option. So you know that for Fick's first law, it is dealing with actually the steady state diffusion, where we do not have a change with respect to time, but we have a change with respect to position of the, for example, if we are trying to diffuse a certain element or certain gas through a bar, so it will depend on the position at which we want to have a certain diffusion flux. So it is dependent on actually the concentration gradient changing with position because it is a steady state. Obviously the Fick's law are concerned with diffusion flux, where we have concentration flux like this. It is dependent on that, and we have the concentration profile as linear. Yeah, which is true because if you see there is a relationship between your concentration and your position, the graph comes as to be linear. So this is also true. So all of the three options are correct. While the concentration gradient does not change with time because this is for a non-steady state, which is Fick's second law, not the first law. So these three options are the correct options. So again, we have this is we have done. Okay, so we have this question that says that the concentration profile for steady state diffusion is given in the figure below. So you are given a concentration profile, as we said, for a steady state we have a slope, which is we have a straight line between the concentration and the position. So you are given the concentration profile and you are also given a diffusion coefficient, which is 6 10 to the power minus 11. So you are asked to calculate the diffusional flux in kg per meter cube second unit. So you simply know what is the value of your diffusional flux. That is nothing but it is dependent on your diffusion coefficient. It is dependent on your concentration gradient, which is the differential of concentration and the distance, because we are talking about steady state. It is something like this. So for a diffusion coefficient, you know the value. It is 6 multiplied by 10 to the power minus 11, and you have to see what is the change in the concentration and change in the position of the in meters, right? Because we have to calculate in kg per meter cube second. So based on this graph, you can see what is the difference in the concentration. So you have an initial concentration that is very high. That is like because we are talking about this, so we can say we have a initial concentration at uh, this, and then we have a final concentration. So we can have a difference in your concentration, that will be 2, because it is 4 minus 2, so it will be 2. And we have to say what is the difference in your distance, which is 10 to the power minus 3. So this is your flux, so you have to just calculate it. So it will be 112 10 to the power 11 and 3, it is minus 8, which you can see from the options. It is it is actually 1.2 multiplied by 10 to the power minus 7. So that is your answer, which is option C. Is it clear? So now we can move to the next question. So these are the questions that are based on your phase diagram. So the first question says that solidus and solvus lines are the boundary between. So you know we are talking about binary phase diagrams where we have two components A and B, which are forming a binary phase, and they are forming some solubility diagram. Like we have a phase diagram. It says if we have two species, we have A and B, and this is the phase which is having a minor solubility of B, which is a maximum showing the maximum solubility of B in A, and we have a liquid phase. And in between these two phases, we have a mixture of our alpha, which is the solidifying phase, and the liquid phase. While here we have a mixture of both two solid solutions, which are alpha and beta, say for example. So you are given what is the solidus line. So in this diagram, if you see, this is your liquidus line, and this is your solidus line, and this is your solvus line. So you have three lines that we are talking about. Liquidus is nothing but it is a phase boundary between your liquid and the solidifying portion of your mixture, which is the solid alpha, and the liquid which is L. While as the liquidus line is the solidus line is the phase boundary between your liquid and alpha phases, or between your say solidifying phase, which is the solid solution alpha plus beta. And your solvus line gives you a indication that what is the maximum solubility of your component B in component A. So you have to say which of the following is true. What is solidus line and which is the solvus line. Since you can also, this is also for a, this is because I have drawn two phases. If you have a single, for a better understanding, you can have a phase like this, where we have a liquid, we have alpha plus liquid, and we have alpha. So we have only one phase here. So now you can say what is the solidus line. This is your liquidus line. This is your solidus line. So you can now say what is the right option. You see, this is the solidus line. So this solidus line is actually a phase boundary between two phases, which is alpha plus liquid and your say for example alpha, right? While as your this solvus line, it is a boundary between your alpha and alpha plus beta. So this is the solvus line. So you can see this is the right option for this alpha and alpha plus b. But for a solidus line, we have to choose between alpha plus liquid and alpha,
Alpha.
not alpha plus liquid and liquid, right? So this is actually a liquidus line, not a solidus line. So this option seems to be right, but it should only have been alpha and liquid plus alpha, then it would have been right. So the right answer for this will be I think none of the above. Okay, is it clear?
Yeah.
Okay, so I want you to do the next question because it is very easy. So you have to see, for a three component system, if the degree of freedom is 3, then what will be the maximum number of phases present at constant temperature? So you have to calculate using Gibbs free rule what is the what is the maximum number of phases that can coexist. So you can calculate and tell me what is the right answer. So you have to use the formula, which is the Gibbs free rule. Based on that, you can calculate.
Formula is F is equal to
Yes, the formula I'll write here.
yeah.
That is equal to F is equal to C minus P plus, because we are concerned with the metallurgical processes that are carried at a constant pressure, so one of the variable is fixed, so we are only talking about one, that is temperature, so 1. So you have to see what is the degree of freedom. This is given, this is 3. You are given a 3 component system, so component is also given, so the number of phases you have to calculate.
It should be one, one, right? Yeah.
Right, so the answer is 1. So what does it mean? It means that you have only liberty to change one variable
Hmm.
without changing the phase, right? So you can change one
Yeah.
variable in a phase boundary, in a phase diagram, and you won't be ending up in another phase. So you have only a possibility of changing one variable. That is what you like. Sorry, you have a possibility of changing three variables because this is the degree of freedom is 3. The phase is 1.
Yeah.
So you have possibility of changing three variables, and you can achieve you will be having the same phase.
Yeah.
So
Okay.
this gives you an idea how many parameters you can control when you are running any metallurgical operation. So for example, you have diagrams where you have temperature, pressure, you are also having the composition variations. So that or you have partial pressure variations. So these diagrams really help you to see what operating conditions you should keep to have a particular phase. Okay.
Yeah.
So okay. One second. Diffusion coefficient. So you understand that your diffusion coefficient is having some relationship with its like how it is varying with your temperature. So based on that, we will have some question. It is saying that the diffusion coefficient for copper and nickel. So you know that copper and nickel can form a alloy, or they can be miscible in one another. So you have two species, copper and nickel, two components, and you are given the diffusion coefficient at 1200 degrees Celsius and 1400 degrees Celsius. So you are given two temperatures and their corresponding diffusion coefficients. So you have to find the value of pre-exponential factor, which is D naught, and the activation energy, which is Q. This is similar to what we did in the vacancy question, the number of vacancies where we tried to determine. So you are just given there we had a variation of number of vacancies with respect to temperature. Here we have a variation of a diffusion coefficient with respect to temperature. So first writing the formula. So we know the diffusion coefficient D, it is equal to D naught, which is what we have to find the pre-exponential factor, and exponential of minus Q by, here we have R, we have gas constant of R and T, right? So you can write for two temperatures, one 1200 and one 1400, the two equations, and then you can equate them to find D naught and activation energy, just as we did for that question. So we can find as D1 by D2, which is equal to RE exponential. So I'll write it here like this, for exponential of minus Q we have to find.
Yeah.
And we have two temperatures, so you have to convert the temperatures in Kelvin. So what are the two temperatures? One is 1200, I think, so that will be
73.
yes, 1473, and we have another temperature which is, that will be 1673. 1673. So now you can find, this is okay, I forgot the R here. So based on this, you know D1 and D2, you know the temperatures, so you can find the value of your Q, because you know the value of R also. R is 8.314 for, if you are calculating it in joules, so 8.314. So now you can calculate the value of Q from here. So what is the value of Q? If anybody can calculate and tell. So have we any answer for this? The value of Q? So this is the value of our Q, which is 387.43 kilojoules per mole. So now we have to calculate the value of our D, which is the pre-exponential factor D naught. So based on that, how will we calculate the D naught? See, the options all had the value for Q. Now we have to calculate the value of D naught. So D, we can simply put the value of D1 and this Q in the any of the equations. So D1 will be equal to D naught E, which is the exponential factor, minus Q by RT, right? So the value of D1 is here, and you have to sorry, the value of your D naught is here, and you can calculate the value of your D1. You can try to calculate the value of your D1.
Yeah. So we need to calculate D naught, right? Not D. D1 is available. D
Yeah,
naught to
D1
calculate.
is given, right? Right. D1 is given, you have to calculate D naught.
Okay.
Okay. So we have to calculate D naught. So can anybody answer what is the right answer for D naught? Because we have the coefficients already given. This was all the same. We have to calculate this D naught actually based on the question. Please try to solve it and answer what is the right answer. Just have to plug in the values of your D1, Q, and R, and temperature is also given. So you just have to find D naught.
So any temperature T1 can be used, right? So
Either you have two options, 1200 and this D1, 1400 or this.
14.
So the D naught will be same because it is a for a standard condition. It does not depend on the temperature.
Okay. (4.5 10 raised minus
4.5 into the 10 to the power minus first or second option.
-3?
Minus 3.
Uh,
Uh,
yeah.
Maybe we should try because I think the right option is first. Yes.
Okay.
So you might have done some mistake. So that is
Yeah.
your pre-exponential factor and activation energy values. Okay. So this question was based on your diffusion coefficients and variation with its temperature. Okay.
Yeah.
Okay. So we can go to the next question. So this is the question that is based on your non-steady state conditions of where we had a diffusion coefficient like for diffusion. So the question says we have a steel sample containing 0.2 weight percentage carbon. So you can consider we have a, say for example, this is our steel sample. So it is having 0.2 weight percentage of carbon, and it is being carbonized in an atmosphere which is having 1.2. So this is your atmosphere carbon, which is 1.2 weight percentage, and this is your zero point 0.2.
Mhm.
Okay. So you are given for a carbon diffusion in austenite, D naught is given. So you are given what is the diffusion coefficient,
Not
and activation energy Q is given. Okay. So you have to calculate what is the depth from the surface of the specimen, because this is your surface of the specimen. So you can say
yeah.
at which composition you have zero point 0.4. So obviously you have a concentration gradient, because as the carbon will be diffused inside your steel specimen, so it will try to increase the carbon percentage. So on the surface we will have a very high carbon percentages, and then it will try to decrease up to like zero point 0.2 it is inside the specimen. So you have to calculate at what distance of the specimen you, say for example it is x, so you have a carbon percentage of 0.48 percentage after you have carburized it 870 at 870 degrees for 110 hours. Okay. So you understand that for a non-steady state, we have a general formula that says that we have something like where we have we have concentration of, say for example any species, here we have carbon at certain time and at certain position which is x, that is given by some formula which is a general formula. We can write it as a minus b, sorry I'm sorry for the one second.
Any easy ways to remember the formula, because this subject has a lot of formulas to be remembered.
Well, the because what you are doing for variations with the temperature, they are almost all are exponentially derived, so they don't have anything to remember. So, like for example, you saw vacancy, so there were the same formula, exponential raised to power the q by r kt or q by rt. So for diffusional coefficient, that will be general formulas. There is nothing you have to strictly remember. You know that whenever there is a variation, it varies with the exponential function. So for that you can remember, but for these type of questions you have to remember, which are like non-steady state.
Okay.
So you have something a
Only
minus.
remembering is only the way.
Yes,
Yeah.
yeah, or you might be provided in your examination. I'm not sure.
No, and they don't provide. So it's the only way to is remembering.
Yes, a minus b, which is the error function x divided by 2 under root of dt, I think. Yes. Okay, so we have a general formula for a non-steady state equation like this, where A is actually your concentration at the surface, and B, we can do the A and B part later. But for this equation to use, because we have to use at a certain position, which is x, so we can find x. So this is actually what is our aim. Our aim is to find at what position we will have
Yeah.
the concentration as 0.4. So concentration is also given, like 0.4 we have to find. We also have a and b values because they are related to your gradient, so we can do that also, but this d is something we do not know. So we only know d naught, so first we should find d. So again, using the same relationship for d, for diffusion coefficient, where we had d is equal to d naught, which is e to the power of minus q by rt, right? If you see this equation, you are d naught, it is given in the question. Okay, this q, which is your the activation energy, that is also given. So this is given. You know r, you know you have to find t. T is also given because you are given a temperature of carbonization, which is 870 degree Celsius. So T is also given. Just plug in your values and find the value of D first. Then we will do the actual part which we had to do with the steady state condition. So first we have to find D.
Yeah.
Okay, so if you can find D, and then we can move to the main part. And try to write the values here so that nobody has any confusion. So this is 2 multiplied by 10 to the power minus 5 exponential of minus 142, because it is kilojoules. 142 multiplied by 10 to the power 3. Remember to take the units in the same form. So this is 1. Okay, and then we have to divide it by r, which is 8.3, because we are joules. We're dealing with joules, so 8.314. It will change if you're having a different unit, so that is fine. And then we have temperature in Kelvin, that is 870 plus 273, so that I can write here. So you have 870 plus 273. You can find easily the value of D now. What is the value of D?
But for this e raised to, right? So the term to be used is e raised to x, right? In the
Yeah, right.
numerator.
You have to use all of that in the exponential form. That is exponential of all of the term.
So that's e raised to x. Yeah.
Yes,
E
yes,
raised to x.
yes, yes.
What is given? Okay.
So we have 870 plus 273. That is 1143. 9502.
870 plus 273. 1142 to 8.314.
Also, It is something like it is 6.47 multiplied by 10 to the power minus 12, and the units will be same like d naught, so it will be meter square per second. So have we achieved the same answer?
6.24 and 10 raised to minus.
Okay, 6.47 into 10 to the power minus 12. Is it right? Okay, so this is your D. So we will write this, we'll keep this D and erase the rest of it. So we can do the later part. I'll write it again. So right now we have value of D. So we will write the value of our D. Am I still audible? Okay, so now we can take this question. So we have the value of D. We can write the value of D first. So that was 6.47, I think.
10 raised to minus 12.
Yes, 6.47 multiplied by 10 to the power minus 12. Okay.
12, yeah.
So you have the value, now you have to use this equation. So for C x at a position of x and at a time of t, so we have it as 0.4. So we write 0.4 for this. Okay.
Okay. Yeah.
For A, we know it is actually the concentration at the surface, which is CS, nothing but CS, concentration at surface, which is given here as 1.2. So you can write as 1.2.
Okay.
minus B is the difference in the concentration at the surface and at the center. Like what is the concentration we start with and what is the concentration that is at the center. It is simply the gradient Cs minus C naught. The gradient which we
Okay.
have to follow 1.2 to 0.2.
0.2. Yeah.
Okay, so we can write B as 1.2 minus 0.2. Okay, so we now have the value of B also. So we have to write this ERF. This is a error function. So we write it as such because we have to solve this. So we write it all of it as such because we do not know x, but we know value of d. So we'll first write it like this: 2 under root of dt. Okay.
Yeah.
So now you solve what is this value 0.4, 1.2. We solve these part and we will have a value of ERF. So it is something like 0.1.2 on 0.8.
0.2.
1.2 minus 0.2, that is 1. 1.2
1, yeah.
minus 1 will be 0.2 and that will be 0.8.
Okay.
Okay.
Yeah.
So now we have this is equal to nothing but your ERF function, right? So we can write this
ERF.
all of this as
Yeah.
some y, right? This is a y value just to
Okay.
keep it under to understand. Now we do not know what is ERF function, so based on that you are given a table here which is y and ERF y.
Yeah.
You are given certain values against a value of your y to a ERF y. So if you know, if we had actually give here at 0.7707, so we could have said that the value of y is 0.85, right?
Correct.
So now we
Yeah.
are given only 0.8, which is not
Yeah.
any of the value. So we have to interpolate this 0.8 to inside in this table and get the value of our x. So you can see this is 0.8 and 0.82 is given. So it is somewhere here between 0.79 and 0.82. This value in the table will be here, 0.8, right?
Okay.
So you have to find the corresponding y value for this. So how will you do that?
Okay.
You will just interpolate it. So how is the interpolation done? So for example, I
0.82
will
minus
take this
0.79.
value and
Yeah.
I have this y value which I have to find.
Yeah.
And I will take this initial value and this 0.8. So I have 4 values, 2 for the ERF y and 2 for the y values. So
Okay.
we will go for the interpolation method where we will try to see what is the value of this y. So how will we do that? We will take, say, for example, you can also take this value because this is the middle value and we have to take the extreme values.
Okay.
Okay. So now we have the value of y.
So can we do this way? At 0.8209, it is 0.95. At 0.8, what it will be? Yeah.
Yeah, that is what we are trying to do.
Oh, okay.
We are trying
Yeah.
to see what will be the value for point exactly at 0.8 because there is a very minor difference in the values. So exactly at 0.8 values, what will be the value? We know for other values, it is a simple linear intercept method
Linear
actually.
interpolation.
Linear,
Yeah, fine.
linear interpolation.
But
So
what we have to take is the extreme one, not the
you can take
before
the
one. Yeah.
near about, but you will have a slight
Okay.
difference. So mostly we take like it is. I prefer to take the extreme one.
Extreme.
Okay.
Okay.
So y minus the 0.95 first. Okay. Then we can take this 0.95 minus 0.85.
Okay.
So this is our one side. We have to do the same for the other side. So for the other side, the same procedure. We subtracted y with our final value, right? Or we can do it for the initial value to have positive values. Y minus 0.85. Here we can do 0.8 minus this 0.77.
Yeah.
0.7707 and you can divide it by 0.82 because I want extreme two values 0.09 minus 0.77. There will be a slight difference between any other value, but no issues. You can take the 0.9 and 0.95 also. That is also possible. That is also right. So you can have to find just the value of y here now.
Yeah.
So you can get the value of y. I think it will be around 0.90. I have calculated it, so it is 0.902. Okay,
Okay, ma'am. Yeah.
so this is your y value, but in your equation what is y? All of this.
Yeah.
So you have to equate it to x divided by 2. You know d, you know time, you know also time
Yeah.
because you are doing carbonizing for 10
Yeah.
hours. So you know d and t. Just put the values and get the value of x. So you can tell me what you get the value for x, because this is important, that at what distance you will have a 0.4% carbon. This is very important. So this will give you an idea that how much thickness you can carbonize for a steel sample. Like what is the magnitude, in what scale it comes, because this is very important if you got heat treatment or you're going for hardening of the steels. So this will help you to understand that how much thickness is that layer, that we are saying that the mechanical properties are improved because of
Yeah.
carbonation. So you can find x value. You can take 1 minute and find the x value. Just put the values and find it. Remember, you are taking the values of your d in meter square per second. So you have to convert your time also uh, in seconds.
Oh.
So we have any answer?
0.014, ma'am. Make something mistaken.
In what units have you got the answer?
Ma'am, I converted the 10 hours into 600 seconds. So,
Mm-hmm.
and yeah, 6.47 to 10 raised to minus 12 root of that into 2.
Mm-hmm.
Then that multiplied by 0.90.
Okay.
0.0142, or maybe I made some mistake in the calculation.
Well, I think I am not really sure, but it is answer is around like 872 micrometers. So you
Okay,
can check it, but
cross check it.
I just want
Yeah.
to emphasize on the scale. Like it is a very small distance that you have actually been able to achieve a carbonization of 0.4%, because outside is 1.2.
Okay.
So it is almost half. 50% of the carbonization has happened, but it is at a very small scale. So you have to understand that these processes are occurring, the diffusion is occurring, but you are not carburizing the whole surface. This is surface hardening only. So the surface, the magnitude of the surface is very small. So that is making a very huge difference in your properties and in your further like mechanical effects. So this was to emphasize here. So you can cross check what is the right answer because I'm also not sure. So okay. Then we'll have another question. This is again the same based on your diffusion coefficient and your like you had the relationship that was varying with your temperature. So now you have given at 300 Celsius the diffusion coefficient and activation energy for copper and silicon are D1 is given because this is your diffusion coefficient. Your activation energy is given, and then you have to calculate the diffusion coefficient at 350 degrees Celsius. So you are given at 300 one diffusion coefficient D1, and you know QD also. So based on your equation, what is the equation? That is D is equal to D naught e to the power of minus Q by RT. You know all of the parameters. You know D. You know this. You know the value of your activation energy. You know the value of your temperature because this is 300. So you can calculate D naught from the first part. Once you have calculated the D naught, you can calculate the D2 further at 350 at another temperature, right? So you can try to find first D naught for the equation. So that will be, you have to find D naught. So that will be 7.8 multiplied by 10 to the power of minus 11 is equal to D naught e to the power of minus 41.5 to the 10 to the power 3 because kilojoules. 8.314 and your temperature 300, so that will be 573. That will be 1 point, so we'll have D naught equal to 7.8 multiplied by 10 to the power minus 11 divided by 1.64 to the power minus 4. You can do this way also. You can do the similar way that we tried to do earlier where we had D1 and D2. You just divide D1 and D2 and then you can find your this exponential function as again the same thing that we did earlier. This is a better way to do it.
47355 into 10 raised to minus 11.
And you can put it in for to find D2. Yes, that is right. You can find to D2.
Okay.
So you can use this equation also, which is much easier to do because here you do not have to find D naught.
Okay. Directly you can.
Directly you can put. So you using your D naught, you can find your D2 also. So you tell me what is the value of your D2. That is 4.7 10 to the power minus 7 and again it's the same thing e to the power of minus 41 was it 14 41.5 and your temperature, just your temperature will change into 350 620. So the final answer is
7.74 into 10 raised to minus
so 7 point into 10 to the
7
power.
10 to the power. I think it is 12.
Hmm. You should have a higher d value
Yeah,
because
higher number for.
yes.
Yeah.
So I think find the value of d2 now. Okay.
Yeah.
So now we can move to the next question. So we have yes. So you can say this is the same question based on your vacancies, number of vacancies. Compute the number of vacancies if temperature is increased from 300 to 400. Same thing that you tried to do earlier. Now we have the value of your K is given, the value of your Q is given, the Boltzmann constant is given. You're just increasing the temperature. Okay, so I will skip this question. You can do it. This question
Yeah,
as
ma'am.
as a example.
We have solved it earlier. Yeah.
Yeah. So first, I'll think we can do this type of question. This is also I'm skipping. We can do this in the next class. First, we'll try to do for this binary system equation. It was related to your phase diagrams. So you are given a binary diagram where a liquidus composition is 30% A and the solidus composition is 70% A. What are the phase fractions when the alloy when the uh, phase fraction when the alloy composition is 50%? So you have to find your according to the Lever rule the phase fractions. So you are simply it is better always to construct the diagrams for such problems because they help you to easily understand the problems. Okay, so if you simply have I am saying this is a this type of a
Arbitrary
system.
diagram. Yeah. Okay.
So we have a liquid, we have alpha plus liquid area, we have alpha.
Yeah.
Okay,
Yeah.
so you are given a binary system where liquidus composition is 30% A and the solidus composition is 70%.
70%.
What are the phase fractions when the alloy is 50? So you are somewhere here which has a 50% composition. The solidus composition is 30. So this is your if you draw at a constant temperature tie line. So this is your 30. This is your 30, and then this is your liquidus line. So that is 70.
70.
Now you were at this point. This is your point. So I write it as point A.
Yeah.
This is your composition of alloy, which is having a 50% composition, and then the solidus and liquidus compositions are given. So you have to find the phase fractions. So how do you find the phase fractions for this? You have two phases. One is the liquid, one is the alpha phase, say for example.
Yeah.
Or even if you have two phases, alpha plus beta, the same thing applies. So if you have first phase, say for example alpha, so for that, how will you find? We have to find the value for the based on our Lever rule. So the value of this tie line. So I can write this as B and this as C. So I can write AC, right, divided by BC. Is it correct? And for another phase, your beta, we can write AB because we always take the opposite arms when calculating the phase fraction divided by BC. So we can just calculate it. AC is nothing, that is 70 minus 15, right? So
20.
that is 20 divided by your BC, that is complete line, that is 70 minus 30. So that is 40. So you have 1 by 2.
0.5. Yeah, 1 by 2.5.
If you know the first phase, you can automatically say what is the second phase, that is also 1 by 2. Okay. So I think we can do these questions, and then we have some numericals on Lever rule again, but they will take some time. So we'll do that in next class.
Okay, ma'am. Yeah.
So you can we try to do these MCQs first. So we have which of the following statements about tie lines in a phase diagram is true? Tie lines represent the composition of two different phases at equilibrium. Tie line indicates the maximum and minimum temperature at which a phase exists. Tie line connects points of equal temperature in the liquid and solid phase, and tie line represents the composition of the eutectic and eutectoid points.
C, is it? Tie lines connect points with the temperatures.
Right. So actually, tie lines are drawn at this option is wrong because B option specifically because tie lines are drawn at a constant temperature.
Yeah.
Right. So they have nothing to do with the minimum and maximum temperature. They represent the composition of two different phases is wrong because we cannot say they are in equilibrium two phases. That is also not wrong. So tie line connects the points of equal temperature in the liquid and solid phase is the right option.
Yeah.
Then we have another question that says, what does the eutectic phase diagram tell us about the behavior of a binary alloy? Okay, so you have a eutectic phase diagram. Always eutectic point is something where we have a point which is melt point of an alloy or a mixture. We say two phases which is lower than their individual melting points. For example, lead and tin. Lead and tin
Okay.
have a high melting points individually, but when they form an alloy, they have a very low melting point. So they form a eutectic point. Eutectic point represents an alloy or a mixture of phases where we have a lowest melting point. That is why there is always, whenever you find a eutectic diagram, there will always be a dip in the temperature.
Okay.
So
Okay.
this
Yeah.
gives you your eutectic point. Second, eutectic point gives you a direct conversion from your liquid to your solid. There are no intermediates like alpha plus liquid or beta plus liquid phases. It is a direct conversion of your liquid solidifying into two solids, alpha and beta.
Alpha and beta.
Okay, so it
Yep.
says that it shows the composition and temperature at which the alloy undergoes a phase transformation. It illustrates the diffusion kinetics of an alloy components. It has nothing to do with the kinetics, but because we are not discussing the kinetics here, because we are equilibrium diagrams, so we are not discussing the effect of time with the change in the phases or microstructure, so nothing to do with kinetics. It indicates the mechanical properties of an alloy at different temperatures. It represents the heat treatment process required to produce the alloy. So based on this also we know
Yeah.
the right option is A, because mechanical properties are also not determined using the phase diagram. We just see what we can do using phase diagrams, but we don't know we don't understand the mechanical properties from the phase diagram. Right? It only tells you the phases which you can form and the properties that phases have to that can be incorporated for your mechanical properties. And heat treatment also we do not decide like heat treatment process is required to produce the alloy. So best option is the composition and temperature at which the alloy undergoes phase transformation.
Transformation.
So we have this question. So we'll try to do these two questions we have. So this and this. So we will try to do it next class. And you can do this question. This is your like assignment type. You
Okay,
can
ma'am.
do this
Yeah.
question.
Yeah.
Okay.
Madam, one question which I had was on on direction on the planes, madam, for the Miller indices.
Okay.
When you get the negative part, like, in the cube, if you say which is a diagonally opposite point you have to take as a origin when you are shifting the origin, or directly opposite to that,
See,
like
it
while
depends what you really want to take. What you have a diagram. For example, if you
yeah,
have a cube like this.
yeah. Because the other day I had asked that question, bar one and one.
Yes.
When I refer this Raghavan, madam, there it is showing differently, but yeah, that's what I got confused on that. Yeah,
Say for example, you have the same what was bar one, bar one?
one,
Zero?
ma'am. Yeah,
One, okay.
one. Yeah.
Okay.
So for this one, to represent this, we should take the diagonally opposite point as origin, or the like the one adjacent to that.
There is no like hard and fast rule to take it. There are situations where you can also do one thing. that this is just a unit cell for your representation. There is a unit cell that is present behind it. There is a unit cell that is present in front of it, on right of it, on left of it. So if you are confused, you can again extend this to another unit cell and make another unit cell, and based on that you can draw your origins again, right? So you can extend these unit cells anywhere. So for example, if I have to draw minus, like bar 1, which is minus of a, normally if I take x-axis from here, right, I take this is my x, this is my y, and this is my z. So along x-axis I have to go to negative x-axis. So you can choose this origin for this unit cell, but if you're talking about this unit cell, you can choose this also as origin. Depends on your which unit cell you're talking about, right? For this first unit cell and second unit cell, the origins are different. This is one, for example. So if I take this as my starting point, so bar 1, but I have to also go bar 1 along y-axis. So I have to go this direction also. So I'll choose this now, because this is minus 1 and this is minus 1 and this is my positive 1. So this is my point for choosing bar 1 bar 1 1. So you can then join them.
Like it. Okay.
Yeah. So that is your
Fine.
plane. So
Understood.
it is actually an extension of the point. Some people even draw a series of unit cells and then draw these directions and planes. Some people just take one unit cell and draw it. So it has like the origin and direction should be just, because it is a plane. So just you have to make sure that the origin does not contain the plane. The plane does not contain the origin.
Origin.
That is it.
Fine.
So the rest you can choose from any point. You can draw at the top another unit cell and draw from here. But it should be correct.
Okay. Okay. So only thing is, the plane should contain that origin. For any origin we can take and then draw it. Yeah.
Yes, you can do any as far as it is correct, because one bar one will have a family of planes. So you can draw any family of, if it is given a family of planes, so you can draw any family of the planes.
Okay, ma'am. Yeah,
Yes.
understand.
Okay. So I
Thank you,
think
ma'am.
that is all for today. Okay.
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 Yeah.
Thank
Thank
you.
you.
Thank you.